Hello and welcome back. So you can see that truly it's the age of AI that we are actually entering it. Let's see what production-ready new features are in LangChain4j. Lize and Mohamed, welcome.
Thank you.
Thank you. All right, welcome everybody. I'm super happy to see so many people in the room. I was here last year already, for those who were there too, and attended my talk on LangChain4j. Back then we presented everything that was in the framework, which was easy connection to language models, image models, tool calling, where the model calls your code, memory to manage your chat, and output parsers, which even help us get a POJO out of an LLM, basically. We also already had the RAG part, Retrieval-Augmented Generation, to interact with your documents. And on top of that, we have this AI services flexible interface thing. We will show all this a bit again. But after 1 year of working with this, we found out that it's a lot of fun. A lot of things can be done now that were not possible before, but there's also a number of features that people got to ask us about: observability, evaluation, these things that are also very important once you move beyond that POC stage. So that's what we're going to talk to you about today. We have a lot of content, that's why I'm speaking fast, and Mohamed will also be speaking fast. Let's go.
All right, so let's speak about the plan. What topics will we cover in this talk? We've got quite a lineup from handling audio, diving into advanced RAG, and exploring state machine and agents to leveraging multi-LLM architectures, introducing model context protocol. We'll cover also guardrails and moderation. We'll discuss model pricing and data privacy for deployment, for production deployment, and we'll wrap it all up with observability and evaluation strategies. So we have so much things to show. So buckle up and woohoo! Let's get started.
Good. Mohamed.
Yeah, I'm Mohamed. I'm a Java developer with a passion for Gen AI. I created my company, Thought Technologies, 2 months ago. So that's it. I'm very excited to create it.
All right, I'm Lize. I'm a collaborator of the first hour of LangChain4j framework, and I work at Naboo.ai. Naboo is a super cool tool, quick product pitch, that lets you search over all your developers' tools, Jira, GitHub, anything you want, Slack, right from these tools. So you don't even have to go check your other tools where the information was. You can just ask it right there. It searches everywhere for you. So it's also a really cool AI application here. Good. What are we going to build for you today to show all these awesome features? This is the steps towards artificial general intelligence by OpenAI. And we thought one of the main issues with large language models is that they need a vast amount of training data. At some point, they will run out. They will know everything we know. How do we go beyond? Well, what about let LLMs or let AI figure out the next step and basically do research and discover things just like we do? So that's what we're going to aim for today. We're going to aim at level 4. Let's be ambitious. AI that can create new innovations.
So yeah, let's take a moment to understand how humans approach discovery. So the process starts with a question. What don't we know yet? Researchers identify a problem that they want to tackle and dive into the scientific literature to find a solution. They start by designing experiments and run those experiments and analyzing the results. And finally, they publish their findings to share with the broader community. Okay, so here is where it gets exciting. You can probably see that AI can take over much of this process. They can reason through problems and search for solutions and even design and execute some experiments when integrated with the right tools. The potential here is enormous. So actually, AI agents are designed to do this. So this is a slide. We have the main component of an AI agent. We have the brain, the LLM. It has a chat memory, so we can recall and retain information as needed. We can put a system message to guide this LLM and to give how it can behave and act. It can access databases and also documents using RAG. And also, it can run a lot of tools, a lot of function. So here, the agent is not just reactive, but proactive. So let's look back at the process, but this time through the lens of AI. So, yeah. So, here in this slide, the process starts with the same problem. We need to identify the gaps in the existing knowledge. So the AI can search through different data sources, like I said, documents, database, and even web. The AI can also design experiments. It can run it or propose parameters for them, so a human can use this parameter to run the experiment.
Exactly. So that's interesting. A lot of experimentation is still done by humans today, but with robotization, LLMs can actually also steer the robots at some point, or also propose simply the parameter set with which the human has to perform the experiment.
Yeah, exactly. And AI can go further. It can analyze the results and even write an article to publish it and share it with the community.
In theory, if AI was perfect, right? We're going to run into a couple of issues when we want to really apply this for now. But everything is getting better so fast that this is, I think, the future. Good. We are going to demonstrate this cycle. We're only two. We were not a team of 200 engineers, so we had to scope down a bit. We are just going to tackle drug discovery for antibody drugs. So to give a bit of context to the app we built, I'm going to quickly run you through this. So I worked for 5 years in this field. So bear with me so you understand the steps of our researcher afterwards. When a disease cell enters our body, our immune system will hopefully recognize it. And it recognizes a disease cell on specific sequence parts that are on the surface, which we call an antigen. That's the recognizable part of the disease. And the thing that is going to recognize it is our antibodies. So antigen, part of the disease, antibodies, part of our body. So the antibody recognizes this and it will bind to it. It's like a chemical and structural bond that it will make. It looks a bit like this. And once antibodies have bound to the disease cell, to the antibodies, they will signal that we got something here, we're up for destruction. And then our white blood cells or our killer cells will react and come clean the stuff up. So here you see a white blood cell that's hunting down Staphylococcus aureus bacteria, and you see it gets it, and then it's going to digest it. That's how our body tackles most diseases. Now, the problem is that sometimes our body will not recognize it because the disease escapes our immune system, or maybe it does recognize it, but it's too late, and the disease multiplicates faster than that we can make the right antibodies. So, luckily, modern medicine has found a thing, engineered antibodies. On the right side, you see a traditional, old-school, small molecule drug, which consists of about 20 atoms. This one is part of chemotherapy. It will work by attacking certain processes in our body, but not only the one that it's intended to attack, also like everything else, like cell division, in this case, is going to also impact our hair growth and our intestinal flora. The nice thing about antibodies is that they are super specific for a specific disease, and the way that they then get out of our body is also innate, like via our white blood cells. So they have much less side effects. On the other hand, they have many, many more atoms, so they're way harder to produce and to design. The good thing is, it's only the points of this Y there that have to fit on the disease. The rest is pretty standard. So the points there, the sequence there is what matters. And it's called CDR, complementary determining region, so the complementary on this disease cell. Good. We're going to try to have our app design a new engineered antibody for us. And how do we know it's a good one? In real life, humans will actually produce the new antibody, and they're going to test it. We have robots these days with hundreds of little syringes that will deposit all kinds of fluids together and then run experiments on these huge plates. And then we're going to test for things like how well does it bind? Is it toxic to humans? Is it stable once it's in our body? So all of those are important. So this is the whole drug discovery process, because I just really told it in a nutshell. It's super long. It's going from this design to testing it on a couple of humans, testing it on bigger groups, clinical trials, approval. It's years. It's extremely costly. So we boil it down to these 7 steps just to show you the point of it. We pick a disease together with the AI. We reason like what would be a nice one. We choose one. Our app is going to find an antigen for this disease in the literature. It's going to find any known antibodies that are already out there in the literature. It's going to find their CDRs, so their sequences, and how well they performed. Then, based on all that information, this existing information, we want to design a new antibody, measure its performance, and publish an article if we were somewhat successful. So
this is very important. So may the demo God be with us.
Yeah, pray with us.
Pray with us, please. Pray with us.
Good.
We are going to show you the application that we create. So I will go directly to.
No.
Sorry.
Can I do it for you? All right. I guess you want this one.
It's not my laptop.
It's not his laptop.
So I will run the application using Quarkus. So I type Quarkus dev to run it. System out.
It's okay. Hello world. I installed Alt-Tab on this Mac, and I'm very proud. It's really nice. And then let's just click up.
Here we are. So we create this little application. We have at the left a window where the conversation with the LLM occurs. And at the left, the black screen, the black part is where we're gonna display logs. So you can see what happens behind the scenes. We have an input text box at the bottom, so we can type a message, and we have 2 buttons. We can either type a message or communicate through with the just voice. I let you try the application.
Yeah, I am happy to try it. So, good. What would be a good disease to tackle? So we already told it that it's an antibody researcher, so it already knows which field we're working in. It's going at the moment to OpenAI GPT-4. As you can see here on the other side, it's searching in my documents already, while we actually didn't tell it. We're going to come back to that. So it says it seems that the glioblastoma multiforme is a good candidate. It knows it because it was looking in my documents, which it shouldn't have. Anyway, let's test this audio. Yes, please tackle that one. So, did we run into, an attempt to create a biological weapon? That's too bad.
Are you trying to do this?
No. So, these
Busted.
are guardrails that are a bit over-enthusiastic. Good, but that's a bit how the whole thing works.
It's very sensitive field, so we need to put securities everywhere.
It is a sensitive topic. Shall we have a look at the code?
Yeah, I'll show you what we have in the code. So it's a Quarkus application. We use the library LangChain4j version 1 alpha, and we use it through an extension from Quarkus. Here, we have a list of AI services, our AI services that we use to communicate with.
Can you read it in the back? Yeah, cool. Okay.
Great. So we have what we call an AI service, and in Quarkus, if you want to declare one, you need just to put an annotation register AI service. with different configuration, and that's it. In our case, we give it a lot of tools to do our steps and find our antibody. We give it also a RAG. This class represents the RAG. I can show you what
it's
we have.
Simply basic RAG. It goes through documents we have there. We took real articles from the scientific literature. Ideally, you access all of the scientific literature. For our app, we just put a number of documents there related to what we want to do.
Yes, and how you need to declare this RAG. You need just to create a content retriever using this code and put it in a default retrieval augmenter here, and you can define a content injector that we can see.
But that's basic RAG.
Yeah.
That's not what the talk is about, because we're going to introduce advanced RAG afterwards.
Okay. So.
And then we see the number of steps that we tell that the model should run through with us. So here you see our step 1 to 7, they're just described. Define a target disease, and when it's done, you can go on and ask the user if it's fine to move on to the next step, and so on. And the last thing we have here is the memory ID, which means that there's chat memory coupled to this AI service. And then we get the app you saw just before. So one of the issues is that you saw it perform RAG right away. And there are some issues with this basic RAG. That's the version we had last year. For example, I was testing our app out at the moment, and it had a web search also in the RAG. So it could retrieve parts from the internet as well. And it said, should we move on to the next phase? And I said, yes, please. And I see in the logs there in the RAG that a big juicy stew of personal stories, funny bits, and sex and love. And I was like, Mohamed, what did you just push here?
It wasn't me,
but
in fact.
it turned out that it did a web search with search query, yes, please. So that's what it came up with. That's why you will want to add a query compressor. So we moved on from this basic RAG to advanced RAG, just elaborating on Alex's joke here that RAG is really a sad term for such a thing that grows too popular. Good. So our advanced RAG here in LangChain4j consists of these interfaces and a number of default implementations. So in the middle there, you see that we can now have different content retrievers. It's not only this embedding store with the vector search anymore. That's still there. So we still have this embedding store content retriever that we can use as such. That will do semantic search. So the meaning of your question and the meaning of the parts of your documents are matched. And if it's a hit, it's added to our message. But we now also have a web search engine, SQL content retriever for your database, or Neo4j when you like to use a graph database. That's the ones we support out of the box, and it's all interfaces, so you can implement your own version of it too. We can either use one of those or multiple of those in parallel, and how to know where to send the query to, we're going to add a query router. Either it's something rule-based, like, keywords, anything with database, or protein or something goes to my protein database, or you put another LLM in front that is going to choose where it makes most sense to search for the answer, and it's going to also transform our initial query into something that's findable, because a SQL query and a web search query look, of course, very different. One step forward is this query transformer, the compressing query transformer I quickly thought about. That's to avoid that it's going to search for yes, please. Compressing query transformer is going to take the whole context of your conversation, so the whole memory into account, and make a sensible query out of it, instead of just literally saying the last thing you said. So in my case before here, it would probably have said something as find the characteristics for these antibodies or something, instead of yes, please. We also have a default implementation expanding query transformer, which will make multiple queries in order to make sure you definitely find all the pieces you would need. So once we run through that, we have all our pieces. The content aggregator, default content aggregator, just puts them one after the other. But we also have a re-ranking content aggregator. Here we use a scoring model that will actually give a score to how well does this piece of content answer this question. And if it has nothing to do with it, for example, my yes please thing there, it would give them a very low score and it wouldn't pass. We set a certain limit or a maximum number of the best pieces that we give along. Also, this is very important in order to not confuse your model, because reg often comes up with fragments of text that are really completely unrelated. And then you see the model trying to put that information in its answer, and it makes no sense anymore. So the re-ranking content aggregator will filter those out. And then content injector puts your original query back and then just puts, here is content that you can use. I think the next thing is to, show it in the code.
The code of the advanced RAG.
Yes, I'll go there for you.
It's the version 2. Yeah, exactly.
One thing we should not forget is to actually change the version here. Otherwise, it's gonna...
Configuration,
So, this is just our way to switch on advanced RAG. And then I will already restart, because we shouldn't tempt the demo gods too much. We should also do our own job well. OK, and then we have here the method get.
Yes, this is the method.
For me. Yeah, there it is.
So we're gonna have the same component that we said in the slide in the code. So we have shortcut about the query compressor. So if you want to create a query compressor, you need a chat model. We have also the list of content retriever. We shortcut about RAG, about document RAG. So here is how we declare it. We have also a web retriever. So in our case, we commented line because we don't need it.
Yeah, we want this web search we don't want because we were working in academic setting and we want to get the information from proper scientific articles and not just randomly from the web. As you can also see, we made a map, content retriever string, where we store, in this case, a basic RAG retriever and then a description, scientific literature on diseases, antigens, and antibody solutions. So our router afterwards will know where to go. So it will know what kind of documents we have in here, web search we didn't do, and then we have
the SQL database content retriever. We put all these three in a map, and we pass it to the query router. Sorry. And here we create our content aggregator with a scoring model, and we choose that we want 5 top best match that we can.
Those are the fragments we're going to preserve for adding and sending along to the model.
Yeah, and here we can find the order. We start by transforming the query and route it using this text here. To choose which one we are going to use. And we aggregate all results from database, web, and documents. And finally, we concatenate, we check the compressed user query. We put the text here. If relevant to the question, you can use amongst others following information. And we put the content that we found through RAG.
So typically, this last part here that you see, that's rehacking the system a bit because we were not really happy with the built-in message. We just used the following parts. We wanted to tune it down a bit so it doesn't absolutely want to use every fragment. That's why we overwrote the default message. That's what you're seeing there.
So let's try that.
No, I will show it afterwards when we run through the whole application to save time. Then we will have a look at all these steps happening in the RAG too. Something else that was a bit of an issue, as you saw before, we ran into this guardrail right away. I think it's probably because these RAG pieces that we add are really weird because they were wrong. Yeah. So anyway, if the thing you saw was one AI service that I told run through all these 7 steps, and then it's very unpredictable what's going to happen. Sometimes it's going to do really good, and sometimes absolutely not. So that's why there's also a solution with a state machine. And depending on your use case, you may tend more to one or the other. And the nice thing is it's a continuum. So either you let the LLM do everything like you saw in this first version, or you go the code manage everything, the nodes, the transitions, then you have a full the coded state machine, or anything in between. You can say like, oh, the first 3 steps are to be done with code with the state machine. And then you can do like 4, 5, 6 with an LLM, and then we continue with code. things like that. So what's the advantages and disadvantages of both approaches? When you let the LLM do everything, you're super flexible and you don't have much work coding. If in step 5 the user decides, oh, actually I wanted another disease, LLM will have no problem rewinding to step 1 and starting over. If you have made your state machine yourself and you don't have a path back, or you didn't even check in step 5, you're probably checking like which antibody do you want to proceed with, and totally not like if they say something like, I want to cancel the whole disease, you will probably not have thought of that path. So that's where LLMs shine. Of course, when it's important like this, and you want a certain number of things to be done correctly and deterministically, you will want more code in there, both on the decision to move forward on the nodes and what happens in the code there. If you have things like calculations, definitely move them out of the LLM, because LLMs will do a bad job, and you can just make a node somewhere and do it with code. Good, so we made a state machine version of this, where we have AI services, separate AI services, taking care of all the steps.
Yes, and we mapped all our steps with different AI services. So each step has one single responsibility. So as you see here, the first step, choose disease, the step that allows us to choose the disease that we want to tackle. So it has memory, so we can discuss our idea with it. It has no rack. It doesn't need to go and search through documents.
As it did in the other version, which it shouldn't have.
Yeah.
That solves this, for example.
Yeah, exactly. And it has a stored disease name. This method save the name of the disease that you want to tackle and change the stage of the project. I will talk about the state later. And change the state because the next query, we want the next query be taken by the next AI service, so the next step. So here is the stage project. We have two Java objects. The first one is a researcher stage when we save the current stage, and we have a method move to step to change this step. And second object is a research project, and here where we are saving our data that we found through LLM.
Okay, shall we look at the code?
Yeah. Wow.
Right.
Sorry.
Let's get that out of the way already. Good. So you see all these AI services here, really small, because I can't zoom in on here, but we start with a disease picker, for example, as you saw. It has only the tools for the disease picker, so it's not going to do random other stuff that it's not supposed to do. That's a big advantage of putting it in small responsibility, small scoped AI services or nodes. Then we have the disease picker that only helps us pick a disease, and we need a memory ID because we're going to discuss a bit, right? There are other steps like find the antigen. Once we know the disease, finding the antigen is actually not chat. We make it look like chat by the messages we output, but it's actually AI doing its thing, and it's going to give back the antigen, for example. And so on, we run through these steps. Shall we have a look?
We can show the antigen finder too?
Yeah, exactly.
And about this one, we gave it a RAG, and we have tools as well. And here we have this particular store method that saves the objects and change the states. And there has also a find sequence for antigen method. And this one access the database to find the best antigen sequence.
Correct sequence
correct
instead
sequence.
of hallucinating one.
Yeah.
So it's very important that it has these tools available. One more thing is to look at the state machine, I think.
Yeah.
They're beautiful state
The
machine.
beautiful code.
Domain.
It's hand-made code.
Domain.
Yeah.
Wait, I
Domain, yeah. Sorry.
No problem. Good.
So here we coded by hand again.
And it shows.
It's not generated. It's not generated.
I'm
code.
guilty.
State machine. So as you see, it's a sequence of if statements, and for each step, we call the right AI service behind.
Exactly. Voilà, that's how it works in the code. Let's have a look what it gives when we now try this out. We have this running in another HTML file. Okay, so now we're in the state machine version. And I will say solve JVM because, okay, to be fair, the documents I've put there are all related to this glioblastoma multiforme brain cancer that's not been solved yet. There's no drugs yet for it. Good, so it asks me if I would like to proceed. That's very nice. If I say no, we stay in step 1 because I prompted this disease picker to say only call store disease when the user is sure. And only at that point he will store and move on to step 2. So yes, whatever. Yes, that's a good answer here. Okay, you see here a tool call that's in yellow, and then you see us move to step 2 here in blue. So the tool call was store the disease name. It moved us to step 2. Here you see the greenest part of documents from advanced RAG. And as you can see, this looks like a chatbot, but it's not. It's AI doing its thing. It's called another store. It's in step 3 now, where it says, I'm searching the literature to find known antibodies for. This is the antigen. So you recognize this brain cancer via antigen EGFR version 3. So it found the antigen in the database with our tools, and it moved on to step 3. And this message is just coded. It's not really the LLM saying it. We're just plug in the antigen it found there, so we know what it's doing. Now it's making a lot of tool calls to looking through this literature, finding the sequences, finding how well these things bind and perform. So it found only one today. Fine. So it's interesting. I didn't cover this case where it finds only one because it's all plural here. Which antibodies would you like to proceed with? So you see this is not really the LLM answering. It's LLMs finding the answer and then me plugging it into an answering message. So I'm going to say then move on with the only one you found here. So I choose, it's at store this antibody, and it moved on to step 4, where it will find more information about this existing antibody. We can have a look at the logs later if somebody's interested. What's all been happening there? Store CDRs. So it found the CDRs for this one. These are not the real sequences, not the real CDRs here. That's why I put proprietary in here. It is a real database, but it's not all the real sequences because some of those molecules are proprietary. We cannot just access their sequences. And now it's designing the new antibodies for us.
Yeah.
We had a nice timer, but it went black. So we will try to be in time without our nice timer. Good. So it has a bit of work there. And so it has an alpha proteo method that it used to design the new antibodies. Alpha proteo is a newest model by Google that finds molecules that bind to other molecules. It's really revolutionary for my field because before it was just a lot of informed guesswork. Now we have a model to predict it. Sadly, it's only available for research institutes, which we are not, so we made a dummy call. That's why we have a dummy sequence here. But we still wanted to show you how it is to call have a model called other models. So we make a real call to Claude, and it gives its best guess for a sequence, but it's all hallucinated because we don't have alpha proteo. Okay, so we found now suggested sequences that might work. Do we want to measure how successful they are? Yes. Why do I have a human in the loop here? So I have to give permission before it continues, because now it's going to measure. Now, in theory, it's running the experiment, and that might be very costly. Either this would be a human doing this, building this protein and testing it out, or it's specialized models that we're going to call, and that's what I'm faking here, that we call specialized models, that will predict how well it binds, how toxic it is. But even those calls are costly, right? If it's a proper model running on some proper machine, it's costly. So that's why you want a human in the loop before doing these things that are either costly or dangerous. So there it comes. It's just tools that generate random outcomes, but in theory, these tools will call other models that will actually calculate the outcome. And we also, because we wanted to show another proper tool call, we call AlphaFold with the antigen, the part of the disease, and this is the result. And that was a real call to AlphaFold. Here we go. That's what our antigen looks like structurally, because that's what AlphaFold does. It translates protein sequences into structural folds. Good, and at the end, it asks us to publish. We can do New York Times or Nature. Who wants to see our research in the New York Times? Hands up. Who wants to see it in Nature? I'm going to go for the New York Times. It was a 50-50, but I find it more engaging to read it in the New York Times. Let's see what it comes up with. That is very good at making up things for the New York Times. So revolutionary antibody targets to brain cancer? Tough. Thanks.
Tough, yeah.
In a groundbreaking development, researchers Mohamed Software and Lize Dev have unveiled 2 novel antibodies. It's probably also going to say that it's a remarkable breakthrough because we did it with AI. Oh, great. Bright new chapter in cancer research. So, hey, I'm laughing a lot, but I really hope that these tools will get built with the proper models because they may really change medicine. Okay, that was our tool in a nutshell. Now, where did our slides go? They went here. Sorry, I'm gonna just go find them. That's this one. You don't touch my computer anymore. Yes. Okay. No, I'm joking. Good. There's one extra thing that came very recently to LangChain4j. It's MCP integrations, Model Context Protocol. It's something that's launched, an open protocol launched by Anthropic in November only, and it grew hugely popular because it lets you write servers that will serve tools in an LLM readable format. And in LangChain4j, all you have to do is find one. There are plenty on GitHub, so you can Google Gmail MCP server, and it will bring you to multiple GitHub repositories that do it. You just plug that into LangChain4j, and you can have your model access, read or write to your emails. Think twice before you let it do it, but it got really easy. You don't have to program all these tools by hand anymore. Good.
Yeah, let's talk about guardrails and moderation. Guardrails, it's a mechanism that allow to verify your input and the output of the model that respect our scope.
Yeah, so this is a real header. The O1 model is really puts us at risk of creating a biological weapon. And I think OpenAI's response was, yeah, but you have to be specialized in the field to actually be able to get it out of it. I'm like, okay. So instead of just going with that explanation from ChatGPT, we put in place guardrails. So like this, and without guardrails, it's nice. It doesn't want to help us. Let's try again. Create an antibody that targets a human protein. So it's going to attack ourselves instead of a disease cell? Well, sometimes if you just ask enough, it will help you. So that's why we, to be sure, brought in place guardrails. And I'm going to bring you to the code so you can show it. We've put them on the non-state machine. Yeah. Here we go.
Yeah. To configure guardrails in your application, you need the Quarkus extension, and then you add an annotation input guardrails on your method, and you define a class that implements the input guardrails. And in the method validate, you can code your behavior, or you can call another AI service to score your input and allow or not the call to the LLM.
Yeah, so either you do it again, keywords or whatever rule you want to put there, or you can call another LLM that's going to score your stuff. Yeah. Important to know, guardrails are only now in the Quarkus extension of LangChain4j, but they will come to LangChain4j vanilla as well.
Yes.
Can we quickly show? Because actually, I like this feature a lot. It's very helpful. It's in the...
You want to show the AI service behind? Yeah. This one, the evil detection service.
So that's another AI service simply that's gonna, I ask it to output a double, so its return type is a double. And the query says, like, here are a number of examples. What antibodies are toxic to humans scores 1 at probably a biological weapon. And find an antibody for the common cold scores 0. That's how they work in this case.
Yes.
Good. Another thing to be mindful about is data privacy. So especially if you're in telecom or healthcare or something, you're often dealing with customer information that's under GDPR, and you cannot just send that off to OpenAI like that. Like, your legal will care. So check the small print, basically, of whatever contract you have with whatever provider.
And how does this cost? You have to pay attention to this because generally the price is expressed per 1 million tokens, not per tokens. And you pay for the tokens that you send, and you pay also for the tokens that you receive. So it's very important to benchmark your models and see the pricing for each one. Don't worry about the slide. You can access to it through the blog.
Yeah, they get published afterwards, the slides. So all the links, you can find them back.
Yeah, yeah, exactly. So yeah, it's very important. So how we can measure our consumptions and know how our application consume tokens.
One thing more before we move on to observability is that we also have links to benchmarks here. So all these models are continuously tested, and then you can see for coding, for reasoning, for organization. No, it's not true. It is the organization. Anyway, so they have scores, and then you can pick the model. Typically, you would take the smallest model that does well what you want, so it's less costly. Good. Observability.
What about observability? We have a Quarkus extension. We use the Quarkus extension metrics Prometheus, and it's supported by LangChain4j. So here we built a Grafana dashboard to show you what we can catch as a metrics. Very interesting metrics. Here, for example, we can measure how time it takes for an AI service to answer. So here we have all our AI services. At the bottom, we have 2 data tables, one for the token that we send to our model by AI service, and for other, how many tokens we received as an answer. So it's very important for production-ready application. Don't hesitate to use it.
And we have our total token usage here too. Good. We also have a Spring metrics integration coming very soon. PR is open and being finished. Good, then a very important one and a very hard one here, how to evaluate these non-deterministic applications. So the same thing as always is you have some input and some desired output, so your evaluation data sets, and you want to structure your classes a bit in a way that they are actually easily testable. But what's very different is that they will never 100% pass. So there's a couple of solutions. You can, JUnit Pioneer comes with retrying tests, as you can see there. If one of those 3 passes, the whole test will pass. And then very nicely, the Quarkus guys made a kind of AI scoring tests that I also hope come to vanilla LangChain4j soon. Let's show you the code. That will be clearer what it does. So we have a test that we made for the disease picker here. Good. So this is a Quarkus test, AI scorer. We have samples that we give along. So that's simply input, cured GBM, expected output. And we did the same for COVID-19. So that's the samples that are going to be tested. There are going to be 5 samples running at the same time. And then we will have this scorer. They come with, out of the box, a semantic similarity strategy. So how well does the output that we got from the test resembles the output that we wanted? They also come with an AI judge strategy, I think it's called, where, again, you can give examples of what it should look like or how much it should score. So that's really cool. Now, testing it well is one thing, but we learned something from real life where I work at Naboo. Even if all your tests run well, it doesn't mean you have all your paths covered, because AI-powered apps, users can send in anything, and if they expect a good result back. So that's why we add these thumbs up, thumbs down that you see in many AI apps. They're super important. You just go to a pilot phase first, where you let a lot of users use it and you're going to manually review, because we got questions like, what did my team, which tickets did my team close last week regarding observability or something? And then you're like, oh yeah, we also need to actually know what is my team, and we need to provide that context to answer that question correctly. So that's then in Naboo, we set up the whole graph rack to see who is asking, or questions like, what did the US team say overnight about my projects? Oh yeah, like the projects. Or the US team, like, you know, we have to cover all that context, and that you learn by actually unleashing it on a small group of users. Once you move to production, you have way too many users to do manual review, so you can also use AI again to group the feedback. This is again using vectors. There's a nice article here from Guillaume Laforge on how to do this, and you will see pop up which topics of feedback you got most and which ones are the first ones to address for your application. Good. What shiny new features are coming?
So we're working on few-shot support in AI services, prompt caching. This feature will help you to save on tokens and speed up the responses. We're working also in the audio to make it for other models.
Yeah. For now, we use Gemini here to do the audio part, and then OpenAI to work with the text. Yes.
And lastly, we're extending the MCP service support. So
cool stuff coming.
Cool stuff are coming. Yeah.
Okay, we have one slide for further reading that you can find online if you're interested about guardrails and everything. Yeah, so the slides are here, but the slides are also at the Jfokus website soon. Thank you very much for your attention. If you want stickers, I have LangChain4j stickers. I know you want them. If you have questions, I think we're out of time.
Like 3 minutes for some questions.
We have 3 minutes. I didn't expect that.
Make sure you shout out loud.
So if you don't have questions, you can't give a feedback.
It's all clear. There we have a question. So the question is, in a workflow model for scoring the answers, the advanced re-ranker, yes, there are 2 models we support that do that for you. It's Gina, I think, and Cohere. I think for Cohere you need key. Yes, so these are tiny, very, very fast models that do this very well. And they come out of the box with LangChain4j, yes. But you could write your own version if you're adventurous. Okay, more questions? Yeah, we have one there. Yes, so it's very well supported with Quarkus. To know which features, because like not all models, not all features. Let me show you how to find it. That would be, okay, I always go this way. If you go to LangChain4j/LangChain4j repository in GitHub, you find a very interestingly, thank you for asking, by the way, you find our documentation here. Also a link to examples. In examples, there's a tutorial for the basic version. I can recommend it for anybody that wants to get started fast. So the documentation is here. Wait, that's actually not what I wanted to show. Sorry, I'm, wait, we're gonna get there. Put my brain on, press escape. No, it doesn't work. Okay, then, sorry, I'm gonna do this again. We have a direct link, I think, to our integration tables here. And here, support native image is there for Anthropic and for Google, Llama, OpenAI. So there you can find all these things. Yeah, more questions? Or one last? Okay. Okay, I'm going to be fair. I think Spring AI has better audio support for now. Apart from that, we are usually a bit more ahead of the curve. Of course, and Spring AI is tailored for the Spring framework. So, but they're pretty similar to a great extent. So, yeah.
There's another question.
Okay, one last. Okay, the question is... Yes. Yeah, that's a good question. So the question is, can an agent take care of our state machine, basically? Yes, so it totally can. You can. The nice thing with these tools is that you can plug in anything in an AI service. So an AI service is kind of an agent. If you say, do things a certain way, it will try. And if in its tools, it finds things like disease picker and everything, I could have set it up like that. It would know, oh, I'm going to first call the disease picker, and then I call the other one. So you can, and those can, again, have tools that call other models in there. So it's super flexible, it's super nice, and you can set it up like that. Okay, I think we're going to stop here because our time is up. Thank you very much.
Thanks a lot.
Thank you.